Good morning. Welcome to the talk on optimizing self-solve using intent. My name is Manikandan Sivanesan. In today's world, every day when you are visiting airports, movie theaters, shopping restaurants, you are more likely to see at least one self-solve option available to you. This could be in the form of passenger check-ins at the airports, self-checkout options in the grocery stores, digital order menus in the restaurants. Providing self-serve options for customers is more ubiquitous than ever. This is even accelerated by the pandemic situation because governments are enforcing rules for the businesses to minimize the human touch points. Customers, when they are using your digital product or service, when they have a question about your product, they really don't want to wait in line or in the phone for the businesses to provide answers. They default to rely on your sites for FAQs, knowledge base, or community forums, mobile apps, and virtual assistants to get the answers quickly. The average customer gives more importance to the businesses that values convenience and time saved for the customers. Self-solve tools achieve both of these value propositions by empowering the customers to answer their own questions or issues and satisfying their own need. Now, why this self-solve is in customer service is more important now than ever. Due to pandemic, companies are seeing an increase in the support case load volume. At the same time, organizations are looking to cut costs in downturn times like this. Customer service with the live channels such as phone, live chat, and email, it really costs an $8 per contact, while self-serve channels such as company run sites and mobile apps cost only 10 cents per contact. So clearly, the cost of self-solve is much, much lower than the cost of live channels. In addition to that, customers will always resort to live channels if your self-service options does not solve their issues. Also, the support agents' working conditions also changed due to this pandemic. So when you have a limited, highly skilled representatives, you have to really efficiently use these resources for more complex issues rather than mundane questions such as FAQ. So one has to really efficiently use support agents for really complex issues versus use self-solve options for really low complexity scenarios. The third benefit is achieving customer retention in B2B. So when customer support clearly varies between B2B and B2C type businesses. B2B businesses have very fewer but more significant customers than B2C, and the support issues ranges from simple to more complex. So by combining self-solve and human support depending upon the complexity, you're solving the issues for the customers in a timely manner, and this leads to customer satisfaction and hence customer retention. Now, about Red Hat, so how we are actually doing this self-solve. So to give some more context about our company, we are an open source technology company for enterprises, and we deliver software and solutions for in hybrid cloud infrastructure and automation and management space. So our customers actually varies from use our technical stack and solutions with varying levels of operational complexity. So we help our customers in allowing to operate the software efficiently. So we are a subscription-based businesses, and the value of the subscription comes from our customer portal, and customers access these knowledge resources and documentation and the timely security advisories from our portal. Now, in order to actually deliver the value of subscription, we have to the self-solve is a critical component for our portal, customer portal. And search plays a very critical role in ensuring that the knowledge resources, documentation, and deployment tools are findable in order to achieve self-solve for our customers. So what we want to achieve in an ideal scenario is really when a customer actually faces an outage or that impacts their businesses, we want to ensure that, and if in case the customer actually find out the root cause and find out an error pattern, and when they actually visit our support portal in order to actually like reach access the support help. So we want to actually make sure that this particular error pattern, if it is already solved for another customer, we want that to be available for our, for this customer, saving time and money, and also saving potential revenue, loss for our customers. That's the ideal scenario that we are striving for. And so having a functional and relevant search is very, very important for us. And this is offered through two search interfaces. One is the site search, where this is the site search available for our whole customer portal. This is where actually all the resources are available in the form of search results. And the next interface is the troubleshooting interface, and which I will cover shortly. In addition to the search aspects, search interfaces that are available, there are certain non-search aspects which are essential for delivering the self-solve. So user experience, if you look at our homepage, in this case, we are really promoting the self-solve behavior for our customers, where they can actually like try to actually solve their problem for each of these products. Now, and if they feel the need to open a support case immediately, we allow them to do so. The next part is support workflow. We follow a knowledge-centered support where an issue occurs and a support agent tries to solve this issue. They want to make sure that they solve the issue for once and ensure that this is captured in a structured content so that this can be reused for the next time the same issue occurs for a similar customer, and effectively like available for self-solve for the next future customers. And last but not least, having an effective content strategy in terms of the frequently asked questions, the frequently occurring issues documented for each of these products, and ensuring that the good keyword metadata available with customer goals in mind goes a long way in delivering the self-solve. And in order to actually like deliver this kind of a search platform, to provide the self-solve, it's powered by Apache Solr open source search engine and Lucidworks Fusion. And we have our own custom indexing component that is powered by Red Hat JBoss enterprise application platform. Now, as I mentioned, when a customer actually have a problem, they actually, if they cannot actually solve it through site search, they want to actually open a support case. So an effective case workflow is critical. So in order to ensure that all the relevant contextual information about the product environment where it occurs, this is very, very critical for two scenarios. One is to actually ensure that additional information such as product and environment would deliver more accurate search results, and also having the right information for our customers, for the support agent, to solve the issues immediately without actually having back and forth between the customers. So also there is customers, we want to ensure that if this is a particular rel problem, then we want to ensure that the right attachments, diagnostics attachments are added to the case, so that there are certain critical integration patterns for self-solve that we use as part of the case creation workflow to ensure that we use as much options to deliver the self-solve. So the troubleshoot-based search, this is a specific aspect where specifically tuned for error messages and more problem aspect of it to deliver the search results. And followed by that, there is the frequently asked occurring issues that in a given product, we have specifically a top content in product aspect. And then finally, if there are certain error patterns occurring in the attachments, we have certain rule-based integration also available as part of this case creation workflow. So with all that, customers can always have the option to switch to case creation without self-solve experience if they feel the need to do so. Finally, now when we actually have these, when we want to actually move towards, now we have this keyword-centric and document-centric journey, but we really want to move towards a user-centric journey. So when a user actually visiting the site, they have a goal in mind and they express it in the form of keywords. We really need to optimize the experience by satisfying their goal in addition to returning the best documents matching the keywords. Daniel Tanglang, the author of Query Understanding publication, he nicely quoted saying that searchers really don't care what you have in your catalog or how you organize your inventory for an e-commerce site. They really care about what they want. And we have to ensure that the searchers express their intent and have the experience crafted specifically for the intent. With this in mind, we looked at our search logs and we see that there are like a lot of intermixing between a problem solving aspect of the queries and as well as regular keyword-based searches available in these two interfaces as well. So we really want to understand the motivation of the user providing these keywords and ensure that these two, we craft the experience for these for our users. Now, when we want to actually look at, want to classify the searches in order to actually understand the motivation of the user, this is clearly a domain specific and there is no one size fits all approach. We leverage our top task survey and also our search logs in order to identify, what would be the best fit. So for this particular thing, we really looked at the taxonomy of different searches in other domains as well, where if you look at the web searches, there are like 3 different broad categories, like navigational, where the user has a specific intent to actually land on a particular site like Facebook or Citibank. There is also an informational based searches where user has to actually want to know about a specific topic or a product. And finally, the transactional intent where the user wants to perform a specific action. In case of an e-commerce searches, this is actually quite different, where it's also actually classified into 5 different categories, and each category has a specific distinct search behavioral patterns. For example, when the user already have want to make a purchase for a familiar item without much of a decision making, it is of a targeted purchase type queries, for an everyday item like toilet paper, paper towels, etc. And the next one is if they are more of a short, vague queries and user is just exploring the product space, it's more of a shallow exploration. The third one is the hard choice queries where, there is, if the user wants to actually want to make a purchase where they want to explore all the candidate products before making a final purchase, it's more of a hard choice type queries. For example, TV, bedding comfort, they are more expensive, so it's more of a hard choice. And the fourth one is the major item purchase, where there is an expensive purchase that the user wants to make, but requires some serious exploration, but with very limited choice for the user. And finally, there is a minor item purchase, but which are not very expensive. And you can see the different examples that are for each of these different types of queries. With that said, the same way we actually looked at our own search patterns, and we classified into broader type rather than more granular level. So the first one we looked at our type of search is more of a single word vague type queries where the users are exploring our product component, products component, etc. Like JBoss, OpenShift. These are all different products that are available for our for the customers, where more curated search results and a curated knowledge graph where there is a one-stop shop would be a better fit. And there is this targeted queries where the users are making an identifier-based searches, which are mostly around security advisories and bug advisories. And the last two, which is primarily primarily the focus of this talk, is usage-based queries and troubleshoot-driven queries. So the usage queries, the users really want to know about how to use a specific product or component that are more of an informational type. Say, for example, how do I join rel to Active Directory? That's a specific intent, usage-based intent that is expressed. And the fourth one is the problem solving aspect, where there is a significant error, there is an error pattern where the users are facing, and if the user actually does not actually able to solve, this leads to actually case creation as well. So I'll hand it over to Jaydeep now on how we built our intent classification model.
Thank you, Mani. To provide our viewers with some more context about the various intents and the Red Hat customer portal, let me give you an insight into what the customer portal is. So it is basically a gateway for Red Hat's customers to either find solutions to a problem they're facing with a Red Hat product, that is self-solve, or raise a ticket, that is create a support case to get help with. The customers are more likely to self-solve a problem if they visit Red Hat's recently introduced troubleshooting experience, or formerly known as the solution engine, thus saving Red Hat the cost of providing manual support. According to key findings of a recent survey, 4 out of 5 customers visiting our customer portal are motivated to self-solve on the solution engine rather than open a support case. However, the percent of customers visiting the troubleshooting experience or the solution engine has been insignificant. And this is where the intent classifier model comes into picture. Broadly, we realize that the queries could be divided into usage and troubleshoot. Sometimes we are asked, why did we choose supervised learning over unsupervised? It is easy to see how one could have interpreted this as an unsupervised problem and tried to find all the different latent intents with a more granular approach. However, we chose to keep it at a high level, thus making the data labeling easier, and that assured us of a good quality data set. Richard, the then chief data scientist of Salesforce, echoes this sentiment in his tweet. Next slide, please. The data collection. So this is where we speak about how we started collecting our data and from what time window. We tried to collect the most recent or the most relevant data, and hence we wanted to stay up to date with the queries that the users are using. For that, and keeping that in mind, we started choosing the data from the first half of 2019. So why do we use the latest queries? So Red Hat's products such as OpenShift or Red Hat Enterprise Linux release major and minor versions throughout the year. So a major version would be something like RHEL 4.0 or RHEL 5.0, and a minor version would be something like RHEL 5.1 or RHEL 5.2. The customer's queries are evolving with these versions, and hence we wanted to ensure relevance when we build the first version of our model. I would like to highlight the fact that this model, or the first version of this model, was built in the latter half of 2019, and hence we chose the data from the first half of this year. Where did we get these queries from? They were all logged in Splunk, which is the software that we use. And as you can notice in the snapshot shared on the screen, these queries were not specific to any particular product. Next slide, please. So data labeling was one of the most interesting challenges we faced since we had to build our data set from scratch. Using domain experts and a bunch of keywords, we were able to manually label these queries. It is important to note here that there are a bunch of tools available online for data labeling. However, we chose the in-house approach since it has a higher return on investment in terms of time, effort, and dollars. The keywords highlighted on the slide guide our manual data labeling process. So for example, if you see usage, there are words such as what, why, where, how, install, etc. So anytime we saw a query with these words, we would tag it as usage. And the same for troubleshoot. If you see words like fail, failure, error, etc., those queries were tagged as troubleshoot. We then fed the hand-labeled data set as an input to an active learning tool called Prodigy. This tool helped us label 4,000 or 5,000 more data points, thus enabling rapid prototyping while building our model. As the last step, since we know no algorithm is perfect, we perform some spot checks to weed out any incorrectly labeled data. Next slide, please. All right, so this is where we try to explain the difference between a usage query and a troubleshoot query. The two examples on this slide would give further clarity on this difference. The usage query that says how to install OpenShift describes a user who's trying to install a product for the first time, while a troubleshoot query that says unable to install OpenShift indicates a user who has faced issues while trying to install OpenShift in the past. The usage query or the customer with the usage query would be directed to some documentation, while the customer with the troubleshooting query would be navigated to the troubleshooting experience on Red Hat. In case you're wondering if machine learning is an overkill and that we could have done this by using simple if-else rules or some business logic, then the highlighted conflicting keywords in the troubleshoot intent is a good example of how we may not be able to continue doing this kind of a machine learning model by replacing it with if-else loop. So let's say you have enable and install as two conflicting keywords, but there's a vast number of combinations of these conflicting keywords that could lead to a scope that is infinite and may not be really captured in the if-else loop. If you look carefully in the examples that are shared, you can find some of these keywords highlighted while labeling our data set. For example, enable, error, how, etc. Next slide, please. Data pre-processing. So this is where we speak about how we converted our strings or kind of pre-processed or clean the strings in a way such that the output of the process is something that is valuable to our model. The raw text contains language components that actually hinder the performance of a learning algorithm. Let's walk through this pre-processing sample query and see how we would try to do this cleaning for it. So let's say the query is, hi, please help me with the OpenShift installation. In the first step, we convert all of the characters to lowercase for the sake of uniformity across all queries. In step 2, we remove all of the punctuations or special symbols, such as a question mark, an exclamation mark, etc. In step 3, we remove traditional stop words using NLTK's stop word list. So if you can see, words such as me, with, the have been omitted from the query. And in the last step, we remove corpus-specific stop words such as hi, hello, or Red Hat. Corpus-specific stop words are words that basically most frequently occur in our data set and are not really important to the model. Pandas, NLTK, and Spacey are some of the Python packages that made our lives easier here. Next slide, please. Now we need to transform the human-readable clean text into a format that a machine learning algorithm can interpret. This means we convert the text into a numeric vector. Though we were spoiled for choice, we used the TFIDF approach. It was super fast on our data set. It took a matter of seconds to run through thousands of queries. Since the average query length was low, there was very little scope to use more advanced text vectorization techniques that relied on contextual understanding. The vectorizer calculates how often a given word appears in the string and then downscales words that appear more frequently across different strings. Essentially, it calculates the importance of each word in the data set. But how exactly does this convert words to numbers? This again is best explained by an example. Next slide, please. This is a slightly busier slide, but it will all become clear in a minute as I walk through it. Think of it as a crash course for understanding the TF-IDF vectorization. Say we have two strings in our data set. String 1 is my cat is not like my dog, and string 2 is my dog is like an elephant. We will calculate the TF-IDF or the term frequency inverse document frequency score for the word my in string 1. So the left half of the table, TF, shows the number of times my occurred in string 1 upon the total number of unique terms in string 1, and that gives you a value of 0.33. The inverse document frequency is the log of the total number of strings in your data set, that's 2, divided by the number of strings having the word my, which in this case, again, is 2. And according to logarithmic principles, you get the value 0. You just multiply these two, and then you get a TF-IDF score of 0 for the word my. If you want to create a TF-IDF vector for string 1, you will notice that at the bottom of the slide. Note how the TF-IDF vector's dimension is equal to the length of the vocabulary of the corpus. Next slide, please. This is probably one of the most exciting part of the process, data modeling. We've done all of the heavy lifting, we've done all of the dirty work with cleaning the data, identifying the problem statement, and now it all boils down to the kind of model we run our data through. So here we adopted the Occam's razor approach. So what Occam's razor approach says, customized for data science, is that one should start with the simplest available option and then iterate on that. Keeping that in mind, we chose the linear support vector classifier, or the SVM. SVMs are based on the idea of finding a hyperplane or a line that best divides a set of points into its respective classes. This is easily available on scikit-learn's linear SVC package. But what do I mean by hyperplane and support vectors? The next slide should answer that. So the blue and green dots can represent two classes, our queries of troubleshoot and usage intent. Our n-dimensional text vectors would ideally translate to an n-dimensional space. However, for the sake of explanation here, we've maintained a 2D space and assumed 2D vectors. So what exactly is the hyperplane here? Intuitively, this is a line or a plane that linearly classifies and separates the two classes. And support vectors are the data points that are nearest to the hyperplanes, or the points of a data set that, if removed, would alter the position of the dividing hyperplane. Because of this, they're considered to be critical elements of the data set. Next slide, please. But that was an ideal scenario. What happens when our data points are distributed like this, where there is no clear demarcation or no clear line that can separate the two classes? Slide, please. The idea is that the data will continue to be mapped into a higher and higher dimension until a hyperplane can be formed to segregate it. So basically, if we project the points from a 2D space to a 3D space using a mathematical function, the hyperplane is able to easily differentiate between the two classes. This is where we can experiment with different kernels of SVM, like linear, radial, etc. This is called the kernel trick. Next slide, please. All right, so we went through the data cleaning, we went through the data vectorization, and now we want to see how all of these moving parts kind of tie up and impact the customer behavior on the portal. So as you can see, you first have the raw query, you do some text cleaning with pandas, then you run it through the TFIDF vectorizer, then you predict or detect the intent using the linear SVC. And in the end, if the intent is detected to be troubleshoot, the user is prompted to visit the troubleshooting experience with the help of that purple element that shows up on the screen. This is how, using the intent classifier model, we are able to influence the customer's behavior. Next slide, please. This is important for us to know that we are doing a good job in terms of the model that we've selected. So we compared it to Spacey, which is an open source advanced NLP library. We compared it to Spacey's pre-trained convolutional neural network. And we saw that the latest version of our linear SVC provided an accuracy of 95% that was comparable to Spacey. It was also lightweight and much faster to train. These attributes are essential when we are trying to see or measure the performance of a model in a real-time customer portal scenario. Next slide, please. The results. One way to check the business impact of the classifier is measuring the number of support cases opened. We recently successfully completed our A/B test to test this and witnessed an 11.6% reduction in the test group exposed to the classifier. Thus, this reduction in case creation rate was a good validation of the effectiveness of the algorithm. The next point that shows about the page views and the time spent per visit trending for a decrease indicates that the users possibly found pertinent content more efficiently because of the troubleshooting experience induced by the intent classifier. Next slide, please. The key takeaways. As mentioned by Mani earlier, each customer has varying motives to visit the search portal. Identifying the broad high-level intents of these users is crucial to building a good user experience. The Occam's razor approach of starting with the simplest yet most efficient tools is a great way to get a head start in any machine learning-based problem. This enables rapid prototyping. The pandemic has accelerated the adoption of self-serve or self-help for customers. Thus, the timing is ripe for evaluating and accelerating work on the self-serve or self-help option for your customers. Last but not the least, no algorithm is perfect or guarantees an ideal experience. Thus, it is of essence to always allow the user to easily find the option to open a support case with a human being. We hope this session was informative and helped our viewers understand the importance of intent-based search algorithms, as well as get an overview of how an intent classifier can be built from scratch. Thank you.